two Jareds who had family emergencies to take care of. All right. Okay, now, what I'm going to show you, we're going to go to that FET thing here real quick. This is kind of just to get started on, we're going to get started on magnetism. Okay? Oh, and by the way, the test was out. If you saw your score on Blackboard and haven't seen your test, it's out of 90 points. It's out of 90, so don't panic when you get your 86 or something like that. You did very well. All right. In fact, everybody, all the scores were in the A range. Which is to be expected, I think, and I hope you all learned something. Now, I've got to go to this, and I think we did. Did that come on, James?
No.
No. Now?
Yes.
Okay.
Do we have class on Friday?
Do we have class? No. There's no class on Friday. Yeah. Sorry, I went to the calendar and checked before I canceled it, so I don't have to cancel it. I wasn't going to be it. All right.
There's no class Friday.
Oh, James, that was cruel. All right. I saw that. All right. Okay. I'm going to show you some things from the FET thing. Some of you who, if you're like me and you get on the computer, you start the day, you got to do something silly like play computer hearts or something like that, just to kind of get the brain started. Here's another fun game you can play. It's electric field hockey, okay? And this is just kind of the practice round. Now what we can do here is we're going to make the puck positive. So when I put this charge here, see, that's the force that it's feeling. And as it gets further away, of course, the force gets less. And as it gets closer, force gets stronger and stuff like that. And so what you can do, what the goal is to try and score a goal. So we'll do it the easy way here. And if I have a positive force, now it's attracting. See, now when it's a negative charge, it's attracting. So I'll do it the easy way. And I'll put this force right here. We can show the field. There's the electric field. You can see as it gets closer. Okay? So we'll put the charge right here. We'll put a positive charge right here to kind of give it the impetus. And then we'll say, okay, start. And it should go into the goal, I'm hoping. So it gets started. You know, oh, I missed. I can't believe I missed. Now I should come back. But if not, let's reset it. Let's put this guy up a little bit higher. And then you start. And he's going to go. Oh! He missed. All right, I'll put him over here. Let's get him a little bit closer. Reset. Start. Here we go. Come on now. Oh! Almost. Let's put him right in the goal and start it now. Can you hear me now? There we go. Hey, yay, finally. We scored a goal. All right, good. So wasn't that fun? But that wasn't any fun because we got to do it this way. You got to hear the. There, much better. And you can increase the level of difficulty and stuff like that, and just start to kind of play with it to rearrange your charges so that it'll be attracted to the thing. Start. Okay, I wanted to get around that thing, and it did. Oh, but I needed probably a positive charge down here. And this is totally wasting your time. You didn't come here and watch me play this. But anyway, whoop, oops, had a collision, so you have to start over. All right, but now, what we're going to move up to today is we are going to talk about, we're going to get into magnets. Okay? Now, magnets, they have a magnetic field, just like a charge has an electric field. Magnets have a magnetic field. However, the difference between a magnetic field and an electric field is that the magnetic field, we can't just have a north pole and we can't just have a south pole. You've got to have both. Okay, it's bipolar. Or It's a dipole, exactly what I say. It's not bipolar. In other words, it's not moody or anything like that. But and so as we go around here, and now the compass will point. The red line is showing which direction the magnetic field is going. Okay, the red arrow is showing which way the magnetic field is going. So as I'm right here, it looks like we got a magnet. The north end comes out like this and curls around to the south end. As I bring this over here, it should flip over. And now I'll go ahead and show the field. There's the magnetic field. I don't know if y'all can see that at all. Hold on. Let me go ahead and get it completely dark. There we go. You can kind of see where the magnetic field lines, see the red arrows are pointing out, showing the north direction. And then they come out and they curl around because they're attracted to the south direction. Okay, so they come out and they're attracted, they come around and they're attracted to that south end. Okay? All right, so that's the way magnetic fields work. All right, just to kind of get you to see. And magnetism for a long time, I mean for up until just really almost recently when we've started getting into quantum mechanics, we didn't understand magnetic fields all that much. We knew how, by experiment, we knew how they worked, and even in the old days of the lodestone, have you all ever heard of a lodestone? That was what they used on, they just hang this stone from like the ceiling of a ship or the upper deck of a ship, and in the old sailing days, or just have it hanging there, and it would point, it'd always point with the magnetic field of the earth to north. Okay, so they had these special rocks that they knew, and that's how the Phoenicians and all those people navigated way back when. Okay, and so we've had magnetic, we've known about magnetic fields ever since we've been, out of not hunting mastodons anymore and stuff like that. So, but actually what causes magnetism is fairly new type thing, okay? And so what we're going to be doing over the next 2 chapters, and I'm a little, you will get chapter 23 in lab. So I skipped 23 last semester at my own peril, but I just know that there's nothing on the dental test or on the MCAT that's in chapter 23. You hit chapter 23 pretty intensely in lab, so we're going to do 21 and 22. We'll finish 21 Wednesday. We'll do 22 on Monday and Wednesday, and then, I'm sorry, we're going to have to do another group exam then on Friday, because I want to do the 2 chapters together. Okay, so it'll be on a Friday. Some of you like that better because then you didn't have lab and all that kind of stuff to worry about. So anyway, so there's kind of the general gist of the magnetic field. Now, magnets do funny things. We can make electricity and magnetism. That's kind of the whole unit that we've been working on. Magnets do funny things to charges, but only if a charge is moving. Okay? Only if a charge is moving. If a charge is stationary, it doesn't feel a magnetic force. All right? And we can create magnetic, and that's what we're going to look at today. We're going to look at just individual particles that are moving, charges that are moving, and the magnetic field. But magnets do amazing things. You've probably, did you all make an electromagnet when you were in like grade school? Take a wire and wrap it around a battery. Take a wire and wrap it around a nail a bunch of times, right? Did y'all do that? Y'all didn't make electromagnets? Science standards are slipping. But anyway, all right. But anyway, as you can see, we've got a current going in a coil. Now this is later on. This is chapter 22 stuff. But you can see, hey, we got a magnetic field here that's going through there. And a curious thing happens. If I change that to AC, look what happens to the magnetic field. It starts changing direction. And that's kind of a cool thing, if we get a magnetic field changing direction, because actually what it does is, let's get rid of the compass, is we can make a transformer. Look at that. There's no power source. There's no power source attached to this guy at all. There's no battery or anything like that, but it's actually moving the current. Now watch what happens when I change that to DC though. Watch what happens to the light bulb. Nothing, because it's a constant magnetic field that's just going. Okay? So it's a constant magnetic field. This is all, I'm giving you a big summation of the next 2 chapters. And this now let me change that back to an AC, so we get the current changing. It's going bam, 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 bam. Got the magnetic field flopping back and forth like that. And so that's inducing a current in that other coil. That's kind of a neat thing. Okay? Very cool thing, actually. All right? And of course, if I get that too far away, the current might go away. If I get it way over here, it goes way down. If I get this way back, it covers some distance. It's dependent upon the distance they're separated also. Okay. Let's see, what else? Oh yeah. Now, so you saw that if I have a moving magnetic field, so let's just start moving this guy. If I just start moving him like this, look what happens. It gets a current going. Now the current's changing direction all the time, but as long as I get that magnetic field moving, it gets really bright if I go through there like that. But once it stops, it doesn't work anymore. So, how do we get a generator? That's how, oh, that took all my thunder away. Okay, so a generator, hydroelectric dams, this is how they work. They spin a big old magnet. They get a big old magnet to turn around a wire. And so then what that spinning magnet does is this. So let's open up Bagnell Dam here. There we go. And look what happens. Because of this spinning magnet, we've got a current going through this wire. So we produce power that way. Pretty cool. All right, so, and this is all fairly recent past, well, really we've had electric power. I mean, the guys like Faraday and Maxwell and a lot of Tesla and all that, well, Tesla was actually past those guys, laid a lot of groundwork back in the 1800s, and then people like Edison and Tesla and people like that made it for practical use. And the culminating activity here is, well, I'm going to invite my friend Mike Kelly, who's an adjunct here in the School of Electrical Engineering, he's retired from Kansas City Power and Light, and he's got a neat demonstration on how all this stuff that I'm going to teach you ties together, or that we're going to learn. All right, so there we go. There was a brief overview of the entire next 2 weeks, for the most part. Okay, so, but now let's go back to the basics here. Let's get back to the basics. And you're going to learn a new right-hand rule. I don't even know if you know any right-hand. Do you all know any right-hand rules at all? Oh yeah, that's what. Yeah, we worked on it. We did on torque. Remember when we did torque? Did the right-hand rule? If it righty-tighty, lefty-loosey. We're going to do a new one. It's a little bit different. Okay, it's for magnetic fields. All right, here's the big idea from your notes. I can turn this off now. All right, from your book. Here we go. We've already seen some of the big ideas. But I actually wrote down some notes that I won't follow. All right. Here we go. Okay, so we kind of looked at magnets. We know that there's a magnetic field out there. Now then, let's say we've got this. I'm going to use blue for my magnetic field. All right, so say I've got a magnetic field moving like this. Okay? All right, now, magnetic field's going like this. Now, I'm going to have a positive charge, an ion, because it's a positive E, 1.6 times 10 to the negative 19. He's going to be flying this way. He's going to have a velocity. He's going to be going that way. Okay? All right. He's going to enter this magnetic field of B. By the way, we measure our magnetic field using B, and it is measured in what we call Teslas, after good old Nikolai Tesla. All right? We actually have a name for it. We didn't have a name for, if you remember, we didn't have a name for the electric field for some reason. But for the magnetic field, it's a Tesla. All right? All right, so now, I've got this guy. He's coming up in here. All right. He enters the magnetic field. Here is the right-hand rule. Okay? And this was a bad drawing because, oh my gosh, I can't believe I did this. That's okay. We'll get over it. Here's how you do the right-hand rule. Take your hand, take your right hand, okay? Put your fingers in the direction of the magnetic field. So that's going this way. Now, take your thumb. See how this is perpendicular? Make your thumb perpendicular. That's the direction of the velocity. Okay? So now, the force that this guy feels is going into the board. All right? So he's going to want to go plowing into the board this way. All right? So, in other words, and I think at a Kaplan's course or something like that, they teach you that it's magnetic field your finger, velocity is your thumb, and then you use this, and then this middle finger is the direction of the force. Okay? But I've got to be careful around people. Well, so some people might take offense. But the book shows you magnetic field your fingers, thumb is the velocity, and then this is the force. So no matter what. So let's draw a better one here. Let's do this. Let's draw one we can kind of see. Here's an example. All right, now I've got a uniform magnetic field. What do the dots mean? Which way is that uniform magnetic field going with these dots?
Out of the board.
Exactly. They're coming out of the board. In other words, this is like an arrow. These are like arrows, all right? And if the arrow's coming at you, all you see is the point, right? Okay. So it's coming out of the board. The magnetic field is coming out of the board. Let's get an ion again. Positive. Let me go ahead and finish this. The force of B into board here. So we can finish that thought. Now, let's have him be flying in here. He's got a velocity. He's perpendicular. He's perpendicular to the magnetic field. So we got the magnetic fields coming out at us. We got a velocity going this way. So which way is the force going? Down. Down. Exactly. So the force is going like this. So he's going to go in a circle. Like that. That's going to make him go in a circle. Okay? Now, let's draw the same field. Let's draw the exact same field. It's coming out at us. This means that it's coming out of the board directly at us. Let's put an electron here. This was an ion, positive charge. Let's put a moving electron here. He's going this way. He's flying in there with V. Okay, you don't know this yet, but an electron is going to go the opposite way of a proton. Okay? So he's going to come flying in here, and he's going to go like that. Okay? So if your problems, most of the problems in the book say you have a proton or a positive charge moving through there so we can stay with the right-hand rule. But all you got to do is just reverse the direction of what you came up with. Okay. So let's try another one. Proton and electron with a different magnetic field. That was a horrible magnetic field over there. Let's do this one, just so you get used to the notation. Which way is this magnetic field going, do you think? Into the board. Again, it's like an arrow. So if you shoot an arrow, if I shoot an arrow into the board, then I'm looking at the back of it, the feathers. Okay? The feathers. Okay, so that's going into the board. Let's have our positive ion, again, traveling this way. So into the board, it's going like this, so I kind of turn my hand over. So into the board, velocity is the thumb. So which way is the force going? Up. Just to beat this dead horse one more time. Now, let's try an electron moving in here. Okay, into the board. Electron would be going which way? Down. He's going to go the opposite way of what he did. So it's going to go like that. Okay? Now the rest is just math. Here's the rules. You've got the right-hand rule number 1. This is what we call right-hand rule 1. This is what we were just learning. Okay. But here's when to apply them. Only moving charges feel the magnetic force. Only moving charges feel the magnetic force. And 2, only the vertical component of the velocity feels the magnetic force. Okay? There. All right. So, let's take a look at this again. Let's draw a magnetic field that's halfway decent here. All right. Let's draw this magnetic field. Let's have it coming out at us. No, I don't want it coming out at us. I'm sorry. I want it. Let's have a magnetic field looking like this. Nice uniform magnetic field that's going down. Okay? All right. Now then. Got a proton here going like this. Does it feel force? Does it feel the magnetic force? No. No. The magnetic force that it feels, F of B in this case, equals 0 because it's moving parallel. So, only the perpendicular component. So let's take a look at this charge. The same charge. Let's take a look at this guy. Let's take a look at him. And here's his velocity. He's going a little bit faster. Now, he does feel a force, but only well, let's see, this angle right here. There we go. Let's break that down like that. But the only thing that he feels is the sine of angle theta. All right, so it looks like this. The magnetic force that a particle feels is equal to the charge times the velocity of the charge times the strength of the magnetic field times the sine of the angle. Okay? And if the angle is 90 degrees, what's the sine of 90? 1. The sine of 90 is 1. Okay, so perpendicular gives you your maximum force that a charge can feel. Okay? And so B gives us, so B, it's also, it's a vector too, is equal to the force that is felt over Q V sine theta. So a Tesla is a funny thing. It is a Newton second over Coulomb meter. It's weird. The reason is I got this meters per second here. This is like meters per second, so we just flip it up here. This is actually all a Tesla. Okay. All right. That's the big idea. Those two equations right there. Now, let's go back. Sorry. Let me get out my book here. So I know where I am exactly. So I can make sure we didn't miss anything important. Nope. We're good. We're good. Okay. Particle in motion. Let's raise the level of pain here just a little bit. You guys did a good job of seeing. Let's do this. Let's have our magnetic field look like this. Nice uniform magnetic field. Okay. Nice uniform magnetic field. Got a particle flying through here, positive ion, flying through here this way. Okay, so that one's going in, going this way. So which way is this guy wanting to go? He's going to feel a force, F of B, that he's going to feel is going to go up. Because he's completely perpendicular to that thing. So F of B is going to go up. But let's add something here. Let's add this little thing that we call a velocity selector. And this is the way they get protons and electrons to really move through those colliders and stuff. Even though their velocity selectors are about 25 feet tall and stuff, these huge magnets. Now, let's raise the level of pain. With the green marker, let's do everybody's favorite, a parallel plate capacitor. Let's put the positive charges here, positive, 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 negative, 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 lined up there. Now, what's the F of E it feels? When it goes into when it gets into that capacitor, which way is that positive charge going to want to go? Down. So when it gets in here, what they try and do is make F of B equal F of E. Okay? Get those two forces to balance, and it'll shoot straight through this at a nice constant velocity. Okay. All right. Now then, let's go back. Let's get this electric field. Let's get a B field that's coming out at us. Okay. Let's just look at the motion of a particle. Here's what we're going to do. How did they do this in the book? Let me make sure I get this right. Okay, I've got it right so far. Here's what we're going to do. Actually, that's going to be negative. Okay. All right. Here we go. This is going to be so much fun. All right. I'm going to take a proton. Okay. Got a proton here. Plus E. Proton sitting there. Now the mass of a proton is, what is the mass of a proton? 1.627, I think, or something like that, times 10 to the negative 27 kilograms. Okay.
673.
673? Oh, that's not bad. That's pretty close. All right. 1.673 times 10 to the negative 27 kilograms. The voltage difference here is going to be 2100 volts between this bottom plate and this top plate from A up to B. VA minus VB equals 2100 volts. Okay? And the electric, and we're going to shoot that guy into a magnetic field here of 0.1 teslas. So the magnetic field equals 0.1 teslas. All right. What we want to do is we want to find out its radius. This is how, any of you in your chemistry labs yet worked with a mass spectrometer? This is how it works. Okay. This is how it works. All right. So here we go. Now what we're going to do is we're going to shoot this proton, and we're going to figure out, so it's going to fly through this little hole, because as soon as I release it, it's going to want to get away from this positive plate, right? And it's going to shoot through this little hole, and it's going to enter this magnetic field, and it's going to have a velocity right here. It's going to reach a velocity caused by this voltage change here that's going to accelerate it through here, and it's going to have a velocity, and it's going to be going this way. So which way is it going to want to curve? It's coming out at us. Thing's going like this, so it's going to want to go this way, right? It's going to curve around like this. And what we want to do is we want to find its radius of curvature. That's what we're after. Two things. We want to find its velocity when it enters. In other words, we want to find V of B. What's its velocity? Now, don't get my V's mixed up. This is the velocity, okay? Not the voltage. We want to find its velocity at B. And this we want to find R. Okay? So here we go. All right. All the forces here are conserved. They're all conservative forces. Okay, so therefore, the energy beforehand is going to equal the energy afterwards. So I've got 1/2 mVA squared, which is 0, plus Q VA equals 1/2 mVB squared. This is all stuff we did. This is all chapter 19 type stuff. Times Q VB. Okay? So, this guy's 0. I can find VB squared this way. I get Q times VA minus VB, just brought him over, equals 1/2 mVB squared. And so you get 2Q VA minus VB. This is voltage, this is velocity. It's kind of hard to keep that straight. Over M, the square root of all that equals VB. Okay. And according to their calculations, when I put all that in there, and the Q of that proton is equal to 1.6 times 10 to the negative 19 coulombs. So the Q, when I put that in there, is equal to, so when I get it all said and done, that's 6.3 times 10 to the 5 meters per second. All right. Now, let's figure out what that radius is. Do y'all remember? This is going to go in a perfect semicircle. Then it'll hit a detector over here. That's how the mass spectrometer works. Hits a detector over here, and depending on the mass, you set it at a certain thing, and you set it at a certain mass that you want to detect, and boom, it'll hit right over here. We'll look at that in a minute. But it's going to go in a perfect semicircle. Do y'all remember when something is experiencing a constant force? Y'all remember uniform circular motion from the first semester? Good old. And it feels the centripetal force. Remember what that was? The acceleration was equal to v squared over r. And so therefore the centripetal force that it feels is ma, which equals mv squared over r. Guess what? That centripetal force is the same thing as the magnetic force that it feels. So let's set those two things equal to each other, and we'll figure out what r is. Because we found out what b is. We got the velocity. We found out what the velocity was. Because the velocity is not going to change. That's incorrect. The speed won't change. The velocity is always changing, okay, because it's always changing direction. So the speed will stay constant. Uniform circular motion. All right. So here we go. So what we do is we say, okay, mv squared over r. This would be that b, that over r is equal to, you've seen it once, so I don't expect you to have it memorized at all, QVB. Sine theta. Now, what's the angle here that this is making with the magnetic field? It's perpendicular, right? Because the magnetic field's coming out, the velocity is going straight up, so it's perpendicular. So we don't need the sine. Well, I can put sine of 90 here, just for giggles, which equals 1. So that equals QBB of B. So we can figure out R. We've got it. So the radius equals, bring this over here, mvb squared over qvbb, which I can cancel that and that, and wind up with mv over qb. That will be the radius of a particle entering a perpendicular magnetic field. Okay? That will be its radius. So we figured it out. We've got all the numbers we can put in there. So its radius would actually be 6.6 times 10 to the negative 2. When we get it all said and done, 6.6 times 10 to the negative 2 meters. Okay. Let's see. Let's do a little quiz here. So get out a sheet of paper. And let's write this equation down and talk about it while you guys are getting out a sheet of paper. We'll kind of go over it real quick. Here's what the quiz is going to look like. All right. Here's what it's going to look like. Let's take this. Now look, the radius is equal to mv over qb. Okay? The radius is equal to mv over qb. So, what happens to the radius if we increase the charge? If the charge gets bigger, what's going to happen to the radius? It's going to get smaller. What happens to the radius if we increase the magnetic field? It's going to get smaller because it's going to just be like a bigger force.
B.
Yeah, if we increase B, it's going to get smaller again because that's going to pull it in tighter. Right? It's going to create a bigger force. All right? What happens if we increase M? If it's a bigger particle, yeah, it's going to get bigger. It's going to kind of lazily go around because it's big. And if we increase V, it's going to kind of zip through there and have a lot bigger arc also. So keep that in mind. So here you go. You've got 3 particles entering a magnetic field that looks like this. Three particles. Q1 equals Q2 equals Q3. Okay? And here's what the magnetic field looks like. Magnetic field looks like this. What's this mean? Yeah, it's going into the board. Here's the magnetic field. Particle 1 looks like this. There's its path. Okay? Particle 2, when it's in there, here's 1. Here's particle 2. It looks like this. Okay? And particle 3, let me add a little bit more. Looks like this. Okay. There we go. Oh, by the way, M1 equals M2 equals M3. Tell me this. Rank V1, V2, and V3. And also tell me if the charges, if the particles are positive or negative. Somehow, I wound up with 2. Okay. All right, so go ahead, knock yourself out. That'll be question 1. That'll probably be the only question we have for the day, too. It looks like we have a quorum if all 30 of you here.
Okay, you want us to rank them.
Which one's, ha! If you're going to rank something, you want to go biggest to smallest. Sorry. Yeah, rank them however you want. Let's go biggest to smallest. All right. We get it? What do you think? First of all, are they positive or negative charges?
All negative.
They're all negative. Okay? Which one's the fastest? 1. Which one's next? 3. Which one's next? 2. Good. Okay. You don't even have to turn it in, because you all should have the right answer, and you're all here. So that's easy. It's easy. Easy to grade. Good. Good. Now, they did ask a little more interesting question on they showed this. They showed something kind of cool. They said they had 3, due to radiation, some kind of isotope radiation, got these gamma particles, right? Got these 3 gamma particles. One bangs into, shoots this electron. They've all got the same charge, And they break into 3 pieces. One piece looks like this, kind of spirals in like that. One piece looks like this, spirals like that. And then another piece went flying off like this. Okay? And the magnetic field here is a third charged particle is knocked out of a hydrogen atom and moves forward, producing the long track with a slight upward curvature. Each of the 3 particles has the same mass and carries a charge of the same magnitude. A uniform magnetic field is directed out of the paper. So this magnetic field's coming at you like this. It's uniform, supposed to be uniform, coming at you. Okay? All right. So we've got A, particle A, B, and C. Is that what they do? Or they do AC? Oh, they did 1, 2, 3, of course. All right. They did particles 1, 2, and 3. Okay? Which ones have a negative charge?
3.
Or which one?
3.
3 is the one with a negative charge? Okay, so it's coming at us. The velocity of this one looks like it started going this way. So which one has the negative charge? 1 and 2 both are negative. You see that? Because the magnetic field's coming out at you. They started, their initial velocities started in this direction. Okay, all of them had an initial velocity that started in that direction. So so coming out at you, initial velocity is going that way. So the force they feel is coming down, unless they're a negative charge. Then the force they feel is going up. So these 2 guys are negative. This one's positive. And if they have the same mass and charge, this radius was supposed to be a little bit bigger than this one. So this guy had the highest velocity. So V2 is greater than V3, which is greater than V1. Okay. All right. I think a little review of what it looks like, you'll get it. Now, the last thing is, and I've done the algebra. We've already kind of done the algebra on this. On actually a mass spectrometer, this is the way you find the mass. Okay? In a mass spectrometer. I've done this derivation before, and it always causes heartache, and people go, oh, you're killing me. And so I've decided not to do the derivation. I'll just tell you what it is. But you got to be careful with it, because people make mistakes with this all the time. This will be the last thing we talk about today. We actually got almost halfway through the chapter today. But I want to review the bidding, though, with all the principles that we've learned. So for a mass spectrometer, the mass is equal to this. The mass is equal to the Q, which is usually E, times the radius squared, over 2V times the magnetic field squared. V is volts. So that little contraption that I had drawn earlier, that's the way a mass spectrometer works. Basically what it does is it shoots a particle through a voltage, goes through a plate into a magnetic field, and then it arcs around, and the ones you want to catch, the mass you want to detect, follows a certain radius. Okay? All right. All right, all right, all right. So, let's review the bidding here real quick. The force. And tomorrow, I've got some personal things to kind of take care of this afternoon. Tomorrow, you'll see a homework assignment for Chapter 21. And we'll make it due like Thursday or Friday or something like that. But no penalties if you don't get it done. I haven't checked the Wiley Plus site in a while. Last time I checked it looked like everyone's kind of working diligently. Don't let these pile up on you now. It'll hurt you and be silly to blow your grade over that. All right, now, here we go. Let's see. Let's look at the forces. All right, So the force that a particle feels is equal to Q times V times B sine theta. Okay? So, if something is neutrally charged and careening through a magnetic field, does it feel a force? No. It's got to have either a positive or negative charge. Okay? And when it enters the magnetic field, F of B is equal to that centripetal force, which equals mv squared over r, which also equals qvb sine theta. So we can figure out the radius that a thing takes off, and so we can simplify this down to figure the radius, which will be mv over qb. Okay? So, the last idea I'm going to leave you with to get us ready for Wednesday. All right? So now, if I have a wire, let's just draw a wire here. Okay? It's got a current flowing like this. And I've got a magnetic field, uniform magnetic field here. Like this. Do you think that wire feels a force? Yeah, because current is moving charge. Okay? I don't know if you've all ever seen that little experiment where they got the wires hooked up in a certain way and you run the current and they go ink. They kind of pull into each other. You've never seen that? Okay, well, we're going to talk about it. I might even bring it in. Okay? I'd never seen it either until I studied this stuff. So, and depending on how you have them wired, if one current's going one way and one current's going the other way, then they pull back on each other. But this is where we're going tomorrow, is looking at currents and all that kind of stuff. It's our magnetic fields. Okay? All right. Well, that's good. That's good. These are the two biggies so far. These are the three equations so far that you'll manipulate around. And just remember, charge has to be moving for it to feel a force. And we are done. You can stop filming now. Back to yellow.